Okay, so how's the sound? Can you hear? Okay, good. All right, coming through loud and clear in the back. Yeah. Okay. Can I get a little more bass in the monitor? No one got that. Okay. It was a sound joke. So can I get a little? Never mind. Couple of announcements. So I'm Jewish, but I'm not very good at it. Like Rosh Hashanah is basically the Jewish New Year, and Judaism is such an old religion. The tradition is that you actually celebrate it for 2 days, unless you're in Israel, right? So in Israel, because it's based on a lunar calendar, right? So it starts on the new moon, and if you're in Israel, you know when that is, all right? But it's based on when the moon is new in Jerusalem. So by tradition, you celebrate it for 2 days outside of Israel because you might not know exactly when the moon is new. I mean, if you're there, you know, because you can look up and see. But if you're not there, you might be off by a day. So it's like sort of like a little bit of kind of like, just buffering, just to add a little bit of extra space to make sure there's no error. So Monday's Rosh Hashanah. Tuesday's the second day of Rosh Hashanah. So I don't actually celebrate the second day of Rosh Hashanah, but I somehow got mixed up. So when I made that syllabus. So I was going to not have classes on Tuesday. There's no reason not to have class. We'll have class on Tuesday. Some people I know might possibly have made plans to not be in class on Tuesday because I announced that day. Like you might have scheduled an interview or something. So there won't be any quiz on Tuesday, right? If you're traveling, if you decide to travel, then that's okay. But we'll record it as usual. So that's the new schedule. That's one change. This thing's not working too great. So today, what I'm going to do is I'm going to start off by finishing up the last little bit of the lecture on stochastic gradient descent. So that's the first thing I'm going to do, and then we're going to start covering some other stuff. So Tuesday we covered a lot of ground. We talked about learning as optimization. We talked about a particular optimization problem where you're optimizing the conditional log likelihood of the probability of a label given the class. Okay, so that's called logistic regression. And talk about how to optimize that with stochastic gradient descent. So this is like a streaming algorithm. You keep the model and data, you keep the data on disk, you stream through the data. One thing that's different is you may stream through the data multiple times in your optimization pass. And then I talked about some details. So one important detail is to prevent overfitting. It's usually important, not every problem, but usually it's important to use regularization. Which basically means putting a penalty when your weights get big. And the naive way of doing that actually has really bad effects on complexity. So unregularized SGD for a log linear model for logistic regression is very efficient because you only have to update the weights for the parameters that correspond to features that are actually present in the example. The example is sparse and most of the values are 0. You don't have to ever touch those parameters. But regularized logistic regression you do unless you play some games. So we talked about this trick for doing lazy L2 regularization. And I kind of mentioned in passing that this is something that you should be watching out for kind of in the future when you're working with big data problems. There's often some sort of sparsity that you can exploit. That can make a huge difference in performance. And there often is some sort of trick for keeping your models, keeping your updates sparse. So then the last thing I talked about was something called the hash trick. So the hash trick is rather than keeping your parameters in a hash table, where the key is the string that corresponds to the name of the parameter, in this case the words that you're using as features. What you do is you basically compute a hash code for the feature, right? But then you ignore collision into some finite size array, and if two things hash to the same place, you basically ignore it, which essentially means you'll add up all the feature values for the things that end up in that same bucket. And likewise, you'll end up with one parameter that's associated with all those feature values. Okay? So it's a slightly distorted representation of the original data, but I argued it could be a lot faster and potentially a lot smaller. So one reason it's a lot smaller is because you don't have to keep the keys around. You don't have to keep the names of each parameter in the hash table at all. The other reason is you can make the hash table smaller. And in fact, there's this really nice property because you can control the size of that hash table, right? The size of that hash table is a parameter, and you can set it to be as large as you want, subject to the fact that memory is finite, right? But if you have a harder problem, you can make it bigger. If you need to run the problem on a smaller set of machines, you can make it smaller, right? So the memory that you're using for your model is no longer this fixed external constraint, and you're just going to have to live with that. Now you basically have a choice. Okay, so for naive Bayes, this would be a little bit harder to do because naive Bayes makes this independence assumption. And if we start glomming features together or collapsing features, that kind of clearly breaks the model. So it feels like a bad idea to do this for naive Bayes. It doesn't feel like such a bad idea to do this for logistic regression. And in fact, it's something that people do all the time. So the key thing, this basically now gives you complete control over how much space you want to allocate for your model. You can allocate less space and maybe do a little bit less well in terms of accuracy, or you can allocate more space and get something closer to the kind of baseline. So I'm going to talk a little bit about some experiments about that in a minute. So that's sort of the next topic, which I kind of meant to do Tuesday but didn't. And then we're going to switch gears, just looking ahead. So what we're really moving to next week, we're going to start talking about parallelizing the stochastic gradient descent like learning algorithms. So specifically, this is a tricky problem to parallelize, okay? So when we're doing stochastic gradient descent, unlike when we're doing naive Bayes, right? When we're doing naive Bayes, we're essentially just counting the events. We can do that counting in any order we want. So if I do a little bit of counting here and a little bit of counting there, and then combine the results later, that's okay, right? But in stochastic gradient descent, whenever I look at a new example, it changes the parameters. So since every update depends on all the other updates before it, because that's what the parameters depend on, it's not obvious what happens if you take that process and you split it into two parallel streams that are updating the parameters like somehow independently or in synchronous. It's not at all obvious what's going to happen. Does it break the math? Does it break the algorithm? Does it break the algorithm a little bit, but not too much? So that's the question we're going to turn to next week. So the way I usually introduce this is I actually drop back from stochastic gradient descent to something that's even simpler. So I start talking about perceptrons because the analysis for that is relatively straightforward. And it's also essentially the same kind of analysis that people do, the big boys do when they're looking at analyzing parallel learning methods. So the kind of standard way of analyzing this is in a regret framework. So this is sort of the simplest kind of regret we can do. So we're going to take a few steps backwards, in terms of algorithmics, and then we're going to take a few steps forwards. Kind of hang with me on that. Okay. So so before I go on to these experiments, are there questions? Someone posted on Piazza that there was like some mix-up with office hours this morning. Did that get straightened out? I saw like an email much later than it would have been, helpful to respond to. Anyone know about this? No? Okay. All right. Okay, so these experiments were described in a paper from 2009. A bunch of famous guys. So John Langford, Alex Mola, recently at CMU, now at Amazon. Kilian Weinberger, who's at Cornell, were involved with this. And what this basically was investigation and presentation experimentally of what this hashing trick does. Okay. So here's the problem that they were looking at, right? The problem they were looking at was spam filtering, and they were doing this at Yahoo. All right. So they're doing spam filtering for Yahoo Mail. So there are lots and lots of examples. You can go in as a Yahoo Mail user and you can mark something as spam. There are lots and lots of users. All right. And there are a couple of different options for how you could do this. So you could have one separate classifier for each user. Okay. Or you could have one big classifier for everybody, which just says whether something is spam or not. Okay, and those both have pros and cons, right? So if I have one filter for everybody, the big disadvantage is what's spam to me might not be spam to you. Okay, so if, for example, you actually do have some friends in West Africa that are going to tap you likely in the near future to bring large sums of money out of the country, right, in some sort of legally serendipitous way, right? You might be looking out for those emails, right? If you're like me, you might say, well, that's probably just spam, right? If you're looking for, if you're like a new professor, maybe those emails that say, could you present your work at such and such and such and such, and you'll have to pay all the expenses and page charges and so on and so forth. You might think about those things, and maybe later on you might not. So what's spam depends a little bit on the person that's reading the mail, obviously. Or you can have one filter for every user so that people can disagree. But the problem is a lot of users are lazy and don't label very much as spam, or often don't label anything at all as spam. All right. So then they basically get no benefit from the fact that 99 people out of 100 will believe that this particular email from, say, Walmart is a spam. So there's a third option, which is kind of in between these. So the third option is to build one classifier, but have the identity of the user essentially be a feature in that classifier. Or actually, more specifically, what's going to happen is the identity of the user is going to be used to generate a whole bunch of features of the classifier. All right. So this is basically the idea. And this is based on this really nice paper by Hal DeMay called Frustratingly Easy Approach to Transfer Learning. And this is just kind of scaled up a little bit more. So when we're looking at the spam filtering problem, our goal is to classify a pair, the message and the word, and the user. Okay, so the question is, does that user think that message is going to be spam? That's the classification test. So it's a property of the document and the user. All right, and we're going to have some features that are just message-specific features, some features that are just user-specific features, and we're going to have some that are properties of both the message and the user. Okay. So the features that just depend on the message are just the words in the message. So that's the kind of standard bag of words thing. The features that just depend on the user, well, there's just one, just the ID of the user. We don't have demographic information or something like that, anything like that. All we have for the user of W. Cohen is just W. Cohen, his email ID. Okay? And then the features of the pair are the words plus the user ID concatenated with the words, okay? So this little dot here is supposed to be concatenation, all right? So here's the basic idea then. So supposing I have that mail and the user is W. Cohen, so that's the email ID, okay? So what would the features be? Okay, so there are some features that just depend on the document, all right? And those would be like, dear Madam Sir, blah, 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 going up to investment broker, and so on and so forth, okay? Then I've got one feature, which is basically just my email ID, so W. Cohen. And then there's a whole bunch of features that are my email ID concatenated with a word. So W. Cohen, dear, W. Cohen, madam, so on and so forth, okay? So the basic idea is there'll be two things that happen. So one is if there are words that sort of generally indicate that something is spam, okay, then those words get a high weight for the spam category, regardless of what user they co-occur with. right? So if I have, a word like, investment that's highly correlated with spam, then it will get a high weight just by virtue of this word feature, okay? But a user can overrule that, right? If I actually add some labels to this data set and label some things as spam, then we can start inheriting some values. We can start inferring some values for personalized features, the ones that have my user ID concatenated with them, right? And of course, it might be that some people think everything is spam, some people think nothing is spam, so that one feature that is the user ID can be used to sort of adjust that preference, all right? So, how do you weight all these things, the global features versus the user-specific features? Well, the short answer is you just use logistic regression. So it's smart about figuring out how to weight everything. We'll just give it all these features and let it weight it. All right? So this is a very simple approach to personalizing the data. Okay? So our pipeline here is we'll take this all right? Specific instances of those. All right? And then we're going to do classification. All right, so let's word features that are independent of the message recipient. There'll be one extra feature, which is the name of the user, user123. All right, and then there'll be another 100 features, which are the personalized versions. So this hasn't changed. Okay, but what has changed a lot is the number of features we have. Okay, because if I had a feature like investment before, that was just one word, and of course there are tens of thousands or hundreds of thousands of words that we might see in email, so it's a big feature space. But now I've just blown it up, right? Because now basically every user word combination is a possible parameter. So we have a much, much larger feature space. All right. In the computation on the fly, basically sort of one a vector of some fixed size. And the data set size, there's about 3 million emails, okay, which is a little bit bigger than the data sets you guys are working with, like 2 million documents, but the same range. 40 million tokens, which is a lot. 400,000 users and change. All right, and if you look at the cross product of the tokens and the users, you end up with a really huge feature space. So looking at 16 trillion features after you do the personalization step. So this is a very large scale problem when you look at the parameter space. All right. So the question is, how does this hash trick work? So here's the experiments, and so the nice thing about this being from Yahoo is that the data is probably somewhat realistic. The bad thing about being from Yahoo is that they don't really tell us everything about the data. So what we're looking at here is we're looking at experiments where we fix the probability, we fix the threshold, so the probability of missing a real message and classifying it as spam is 1%. All right, so you're only losing 1% of your emails to the spam filter. All right, and then we're basically seeing what the misclassification rate is on the remaining emails. So how many things are incorrectly, slipped into your real news email stream when they really should have been picked up by a spam filter. So they won't tell us what that number is. Okay, so we have a baseline number that's just like normalized to 1.0, and the question is if you do better or worse than that. So we don't really know what the real numbers are, but we have an idea how we're doing relative to a baseline. And what they do here is they're looking at various sizes of the hash table. All right. So I guess the important thing to look is these hash tables are not huge, right? So even the biggest one, which is 26 bits in the hash table. All right, so that works out to be about 1 gigabyte of space for storing parameters. It's not too bad. Even 2009, that's not too bad. And what you can see here is this is basically just using the bag of words features without any personalization. And you can see that the accuracy converges pretty closely, right? Even, using only, I guess, a quarter of a gigabyte gives you about the same accuracy, right? And you really have to drop the space down. So each one of these 2 bits is like a factor of 4. You have to drop the space down by quite a bit before you start to see a noticeable loss of performance. But the other thing that's cool about this is you can also do personalization. And again, you sort of see, even though the feature space is much, much larger, what you see is you've almost converged at, a billion bytes worth of parameter space. And what you're converging to is something that's quite a bit better than what you had before. So because you're doing this hash trick, you're able to move into this big feature space, which has 16 trillion distinct features. A lot of them are being collapsed together, all right? But it's still okay, right? In particular, we're doing a lot better than we could have if we had to explicitly store the features, right? Where we're really kind of limited to the unpersonalized case. All right, so that's sort of one of the results that basically shows that this technique works pretty well. It doesn't work well when you're like putting things in a hash table and there's only like 1,000 buckets or 10,000 buckets. But if you're in a space where there's millions and millions of parameters, it's okay to set up something where there's, a few, let's say, a few tens of millions of parameter buckets and let things sort of collide. That sort of seems to be a general rule. Here's another interesting study with this personalization. So and this is again looking at the result as you add more bits to the hash table, right? So if we pick one of these here, so to 20 bits, something like a gigabyte. So we're still things quite a lot. And these lines here are basically tell you how much savings there are depending on how many messages you've labeled. All right. Getting some benefit from personalization, which is kind of interesting. So what's going on here is you're sort of decreasing your confidence in the features that are labeled differently by different people, right? And that's happening because some of the weight that the optimizer would have normally put on the sort of user-independent feature weight is now sort of being sucked up by the various personalized versions. So it's kind of an interesting effect. If you look at Haldame's paper, you can sort of see like a discussion of that in a somewhat simpler context. So these are the results. Okay, so A, this is kind of this cool trick for personalization, and B, demonstration that this hash trick works pretty well. Okay, I forgot to mention I was going to talk about this, but say the SGD assignment's going out today. Yeah, I know, one after another. The SGD assignment's going out today, and this is one that in my experience is people have trouble sort of getting it to work perfectly. So I just want to give like a few general comments about debugging. So most algorithms, most systems, nowadays with these typed languages and modern computer languages, once you've got something compiled, then you're pretty close to having something that works, right? So for a lot of things, the debugging phase, it's like once you've got something that actually sort of compiles, it gives you like sort of the output that's syntactically correct, given the input, you're pretty close to getting the right answer, okay? That's not necessarily true for machine learning algorithms. So, I mean, this is something that happens all the time. You read about an algorithm in some paper, you code it up, right? It compiles after a little bit, right? And you run it on the data set that you download from the author's site. You get 87%, which is good, but the author got 91%. So something's wrong. What's wrong? right? You can't go in and say, well, where was that syntax error? What line was that on? Oh, I just threw a null pointer exception. Where is that? It's not obvious what to do, okay? And of course, you know, in real life, you don't know who's wrong. It might be you. It might be him, right? So this is something that happens all the time. So the worst thing, I got to tell you, from a psychological point of view, is it's the other way around. You get 97%, but the author got 91%. So now you're like, first you're really happy. It's like, wow, I got a really good result. And then you start thinking about it a little bit more. Maybe you talk to your advisor and he's like, I don't think so. So you probably have a bug which is making your results look better than they should be, right? That can also happen. So it's hard to debug machine learning software. And the problem is there's this really wide range of behaviors which are almost exactly the same as the correct behavior, but they're just doing something a little bit different numerically. All right. So there's lots of almost correct modes for this program to be in. This is typically a problem in experimental research in machine learning. It can be very hard to replicate other people's work, particularly when it's worked with a complicated system. So if you can actually get hold of their code, then that sort of gets. But in general, it's hard to do. It's hard to make sure you've got an algorithm exactly right. So here's my advice, and this is actually something I think is also kind of hard to teach, right? So my first advice is write tests. Okay, so write unit tests. If you've got something that sort of seems like it's a subtle problem, see if you can write a test that kind of teases that out, right? And if you're still not sure why it's doing it, it's like if you're stuck, don't just stare at the code, write some more tests, right? Then I guess if you're really stuck, then I would say, you know, like just kind of like life advice, take a walk, come back in an hour, sit down with a friend. You know, it's okay to sit down with somebody else in this room. That's as long as you sort of put it in your collaboration statement when you turn the homework in. And it's very often the case that you'll get some ideas as to what's going on when you start talking through things. Okay, you know, taken, it's fine. Okay, and you also might. The main reason we do math for machine learning really is not so much to understand what the algorithms are doing or even to develop better algorithms. Honestly, it's so you can verify what your algorithm is supposed to do, right? So it's much easier to write a test for something that has a clean mathematical statement because you can look at the math and predict what it's supposed to do. So here's some examples of what you might want to do. So let's say we've got a generative learner like naive Bayes. Okay, so one thing I could do if I wanted to test my generative learner is I could just write a generator. Usually that's quite easy to do. So it's going to generate data from the underlying model. So it's got two classes. It picks one with probability, let's say 0.3, then one with probability 0.6. Then it chooses the words according to like two different multinomial distributions I've like rigged up. Okay, and then I can run my algorithm on it, and I can see whether it actually recovers the parameters of the original generator. Okay, if it does, everything's good. If it doesn't, it may be buggy. It may be that there's like a convexity issue and it's just not reaching those parameters. That's also possible. So maybe if you start off close to the parameters, you'll be able to recover the parameters. So a simple problem, the learner will recover the parameters of the generator, and if it doesn't, that's usually a problem. Okay, and it also gives you a chance to kind of test things out on weird cases, right? So if you have like things that are really skewed and there's a lot of weight on one example versus another, then you might run into, I don't know, sparsity issues or something like that you wouldn't see otherwise. So when you're writing tests for a discriminative learner, there's not a model for how the words get generated. So if you're generating, you know, the words in the document with some stochastic thing, the learner's not going to recover that, right? But you could generate the class probabilities, right? You could generate the probability of y given some set of x's. And you see whether it successfully recovers parameters that track that probability. One thing that's really important for any gradient-based algorithm is to look at whether the gradient is actually doing the right thing. So if you compute the loss on the example, which you don't have to do, all right, you don't have to compute the loss on the example to implement this project, right? For this assignment, you don't have to like tell me what the loss is on for each example, but it's a really good idea to compute the loss because then you can look at the steps that the gradient is taking. Well, did it actually reduce the loss on that example, right? When you make a pass over the data, it should reduce the loss over the whole data set on the training data set. Okay. The other thing you can have to do a little bit is, if you think about it, you kind of know how much. Okay. So the gradient of your loss function at some example x, right? You kind of know what that is, right? It's basically what would happen if you just took f and you a little bit. Approximate gradient. So by more than like, and there may be some. So this is actually a really good strategy for debugging gradient-based systems. The last thing I'd suggest, particularly for things in this class, and when the hash station there on the you use a large, small set or a large. It should be a good approximation of what you would get if you kind of use a full hash table. So that's another thing that's very useful to do is kind of this. I changed the battery. Wow.
No, so it's working intermittently?
Yeah, all right. Okay, let's see how it goes. Okay, so the next topic here is basically online analysis. So optimization is one model of how to design machine learning algorithms. It's not always a great model of what you have time to do. So it's often easy to write down a loss function that you'd like to solve, but it may not be something you can actually solve efficiently. So there's another analytic approach that is actually quite useful, which is called online learning. Sometimes the more general version is called regret analysis. So here's a typical case. So in online learning, what we're doing is we're looking at a sequence of activities. So it's not the case, we're looking at one example at a time. Okay, we have the models probably in memory, and we're streaming through examples and looking at one at a time. But we're not doing this because we don't, we're sort of trying to optimize space. We're doing that because that's sort of the essence of the problem as we're defining it formally. So the goal is to, after you see each example, make a prediction. And then you get immediate feedback on the prediction. It's kind of like taking the online quizzes for this class. You make a prediction, you get a feedback right away. Then you get the next question, okay? Let's skip that kind of point right here. So here's an example. Right? So we're going to treat this as a game. There are two players, A and B. A is adversary. So I get to pick the problem. So this is what you as the learner learn. All right. There's some constraints on how that data will be drawn and maybe it's a hyperplane or maybe it's a decision tree. So I know what the rule is, but you don't know what I do is I pick an example and I give it to you, all right? And let's now just assume there's a finite set of possibilities, okay? You predict the label, okay? Pick set of label, you send it. And then I basically grade you, so I tell you if you were right or wrong. And what I'm just going to record is whether you made a mistake or not, all right? So what's going to happen is there'll be this sequence of tests. After you've learned it, you won't make any more mistakes, right? So the number of mistakes will sort of top off, all right? And of course, I might give you the same example over and over again, so you don't really get to learn anything about the general concept. You just sort of memorize that one example, right? So it might be that, in this long sequence, I could sort of stretch it out as long as I want with things that you already know how to answer, right? And you're not likely to learn very much from just repeating those things, all right? So what we don't really care about is how much time it takes before you get to something which is accurate. We care about how many mistakes you make along the way. So what we care about is the your address 605 teacher. That number is called the mistake bound, all right? And it's a little bit surprising there actually are algorithms where you can analyze these things and get a good number, because it seems like a very hard thing to do. Analyzing machine learning algorithms in sort of a statistical setting, right? So the algorithm's converging because things are coming from a distribution. There's no distribution here, right? I can give you any sequence I want, right? This is really just sort of like a purely information theoretic sort of thing. And it turns out there is a very simple and fairly practical algorithm where you can compute the mistake bound and analyze it pretty well, all right? So this is the perceptron algorithm, okay? And this is probably the oldest, well, certainly one of the oldest machine learning algorithms ever. So the idea is basically the following thing. You have a current guess as to what a hyperplane separator is, VK. I give you an example, X. You basically look at the inner product with your current hypothesis, VK, and then you look at the sign. So either it's positive or it's negative, all right? And then you tell me whether you think the answer is +1 or -1. And there are only two labels, +1 or -1, okay? And then I tell you if you were right or wrong, or alternatively, I tell you what the real answer was, +1 or -1, okay? And the learning So the learning is if you didn't get anything wrong, don't change anything. If you got it wrong, then you do this update, all right? So yi, the label is either +1 or -1, so you're basically either going to subtract the example from your weight vector, or you're going to add it. All right. So the claim I'm going to make is that this is going to make a bounded number of mistakes if the adversary plays by two rules, okay? So the first rule is the following, okay? So the first rule is whatever labels I give to the X. All right, so there's some vector u that always gives you the right answer. It will give you positive for a positive example, a positive inner product for a positive example, negative for a negative example, okay? And not only that, it won't give you something arbitrarily close to 0. It will be fairly confident about its classifications, right? So one way of saying that is that the product of the inner product between u and x, all right, and y is always more than gamma, where gamma is some positive number. Let's say 1, okay? So if y is positive, then this has to be at least, if this is +1, this inner product has to be at least I guess, gamma, right? And if y is -1, then if this should be negative, right? Because we want so if gamma is 1, it's got to be, if this is -1, then this has got to be a negative quantity, so it's got to be predicting the right sign. But it also has to be sort of sufficiently far from 0. So if the sign of u dot x times yi is correct, that means u dot x was the right answer. It was the right sign, okay? And if it's larger than some threshold gamma greater than 0, it means it's not too uncertain. Okay, so that's the first rule. And the second thing is, and maybe this is a little bit like regularization, I'm just going to assume that the weights aren't too large. So it works out mathematically, just assume that I'm going to assume the 2 norm is 1. So the Euclidean norm is 1. All right. The other constraint is I'm going to assume provides examples that are near the origin. All right. So the examples are the 2 norm of the examples is less than r. Actually, I'm going to make that r squared. It turns out to be a little bit nicer. Okay. All right. So just to kind of get our heads around this for a second, let's do this with SGD. All right. I can make a prediction. I call it y hat. All right. But once again, it's a sign of my weight vector in the example. Well, not quite the sign. It's the logistic. Right. So it's a little different. All right. So if you kind of think about it, what does this update rule say? Okay. So if y is -1, if there's no mistake, so y and p are the same, then there's no update. All right. If there's a mistake, there's sort of 2 kinds of mistakes. So y could be negative and p could be positive, in which case we're updating my vector by adding -1. Okay. So essentially, we predicted too big a number, and we're decreasing our weights. The other one is our weights were our prediction was too low. So p was -1 and it should have been +1, and now we're adding the example to our weights. All right, so this is not that different from the SGD update. So here, what are we changing things by, right? So if we were smart enough to make exactly the right prediction, okay, so p was 0 or 1, there would be no update. Of course, that's never exactly going to be true, but basically, if y minus p is small, then there's less of an update. So it's kind of a soft version of this. And once again, so here we're looking at 0 and 1, but if y is negative and p is positive, this is going to be a subtraction, right, of x. If y is positive and p is negative, then we're going to do an addition, right? So it's essentially the same sort of rule, okay? What's different is we're moving the vector in exactly the same direction. We're moving it toward x or away from x, right? And what's different is how much we move it, all right? So for the perceptron, there's this sort of like soft measure of how much we agree, and there's a learning rate, and we move it that direction, that amount, right? And here we just move it 1, regardless, okay? And we don't move it at all if our prediction was like qualitatively correct. All right, so this makes a little bit more sense also if we look at some pictures. So here's some pictures. I went to time talk, I guess. So here's a space. So all my examples have to be in radius r. Okay, so if in 2-dimensional space, that basically means they're going to have to be in this circle. Okay, and my secret vector that I'm using to label things is u. So it's just going to be right here on a 45-degree angle. All right, and the rule I'm using is that whenever I give you a vector, it has to be something where this margin rule is satisfied. Okay, so the margin rule basically is this. Okay, it says if I look at the dot product of x with u and multiply by y, then that's greater than gamma, right? So what would that mean for that not to be true? Okay, so the dot product of x and u is basically, I can find it if I give you an example x, somewhere in this circle. The dot product is basically found by projecting x onto u. All right. So if I project x onto u and that projection is more than gamma, it's all fine. And I have to give you sort of the right sign. So if it's on this side, I have to tell you positive. If it's on this side, I have to tell you negative. But the projection can't be less than gamma. So basically, I'm not allowed to give you examples that are in this yellow stripe. All right, so this is basically a separability constraint, okay? So I'm going to give you examples. I'm going to give you the right label, and also I'm not going to give you a whole bunch of examples that are really, really borderline right on this, you know, that could sort of go either way. I'm going to give you examples that are sort of clearly that are easy to separate, okay? And another consequence is I don't have to get u when I'm learning my vector. I don't have to get it exactly right. It's okay if it's a little bit off, because if I just jiggle this a little bit, it will make different decisions, but only on things kind of in that yellow stripe. So that's okay. So let's take a look and sort of see what would happen. So let's say I give you one positive example. So it's this positive example. All right. So the next thing that happens is I will, you know, well, let's say my first prediction I guess negative. I guess 0. So that's always wrong, let's say. All right. So the first thing I'm going to do to update is I'm going to add this example to my weight vector. All right. So now my new weight vector becomes this example. All right. So what does that basically mean? So the next time I get an example, what I'm basically going to do is I'm going to treat this example as a prototype. All right. If the inner product with that example is positive, I'll say it's positive. If its inner product is negative, I'll say it's negative. All right. So inner product you can think of as a similarity measurement. So we're basically sort of saying, is it similar enough to the one example I've seen so far? All right. So let's imagine I get another example. So the hyperplane right now is basically whatever's 90 degrees from this purple line. Okay, so maybe it's this. All right, let's pick an example that is positive but would be classified in. All right, so let's imagine I pick something that's in this green area, but that's not on the right side of that little light purple line. So it's got a negative projection against the other example. So I'll pick one over here, okay? So if I take this x2 and I project it onto v1, then it will get projected out, I guess, somewhere over here, right? So it's definitely a negative projection onto v1, right? So I would say, well, that's negative. It's not very similar to v1, to our previous example. All right, so once again, I'm going to update by adding, right? So I'll take x2, this vector, and I'll add it to this one. So we know how to do that, just kind of do head to tail, and we'll end up with this new guess, which is the sum of these. All right. So that's where we are after 2 examples. All right. So no problem, it's only 2 to the right answer. Okay. Here's another example. I could pick something that's actually pretty close to this v1, but it's a negative example, right? So I could say, well, if I project this onto v1, that's definitely a positive projection. So if I'd given this an example, you'd also make the wrong prediction, right? You'd predict negative. In fact, you predict positive when in fact it's negative. So what we're going to do here is we're going to take this and subtract it from my current weight vector. All right, so again, we take this, we flip it around because we're changing the sign, and we add it head to tail, and we'd end up with this thing, which is pretty much. So this is how the perceptron algorithm would work. So I guess, yeah. So let's take a little bit of a look at what this is doing. So I said this is something we can analyze, and in fact, the analysis is very simple. And if you try even a little bit, you can get it all in your head at once, which is really nice. So the first claim I want to make basically is the following. All right. So I want to basically say that the inner product of my current guess after k mistakes with u, kind of my secret answer, is always at least k times gamma. All right. In other words, basically, whenever I make a mistake, the dot product between vk and u increases by at least gamma. All right. So there's kind of a proof here, just basically by looking at pictures. So let's say I've got an example here. Okay. What I'm looking at is how that projects along u. Okay, so what I'm basically saying is, projection out. Okay. All right, and my claim basically is that every time I make a mistake, that the projection is going to creep along this line by at least gamma. All right? So why is that true? Well, it's true because whatever I've added has a component of at least gamma away from this separating line. Okay? Whatever I'm adding, I'm either adding it or subtracting it depending on whether it is on the right side of the separating line. Okay? So the component along the separation, which is the okay, so the margin. All right. So that's the intuition. Not be easier to look at the math. All right. So to do the math, we basically just take our definition. Okay. So vk plus 1 is basically vk plus yi times xi, right? So that's the update rule. Okay, and what I'm looking at is how this changes in terms of its projection along u. To just add these, so now we're talking hypotheses along u, and now we just have to do a little bit of simplification. Okay, so we can take this and we can distribute. All right. Okay. So now I've got vk.u and vk plus 1.u. All right, and I've got this number right here. Okay, so I'm sorry. The one thing I know is that there's this margin rule. Okay, so the margin rule says that xi.u times yi, the label I give you, has got to be at least gamma. All right, so since this is at least gamma, I can replace this with gamma, and then since that gamma is bigger, then I have an inequality here. Okay, so this basically says this is increasing by at least gamma each time. Okay. Right? Not rocket science, it's basically just sort of capturing this intuition. All right? So this is something like convergence, all right? We're basically showing that we're getting something where the angle, the dot product, the projection along u is getting larger and larger. So in this example, of course, we're also getting something that's really closer to u in terms of its position in space and the decisions it's going to make. But there's another way we can increase this projection, right? So I can increase this projection by just taking v and extending it out a little bit further and then a little bit further and then a little bit further, right? So every time I extend v and make it longer, then that projection also gets larger, all right? So I also want to check and make sure that it's happening just because v is getting larger and larger, just sort of getting further and further away from the origin, all right? So the claim basically is that the Euclidean norm of vk is getting squared. So this is the dot product of vk with itself is growing by r squared each time. And again, this is, if anything, even more obvious. K is changing because the examples have to be in this space. Time it's going. And again, if we want to do math, we can do it pretty easily. So what we care about here is the norm of vk squared, which is just the dot product of vk with itself. So I want to claim this isn't growing too fast. So once again, I'll just write in the definition of vk. That's kind of all I can do. And then I'll do some distributing. So now I've got the norm of vk squared here. We've got, if we look at those two products, it's y squared times the norm of xi. All right, and then here I've got this thing right here. So 2yi xi vk. All right. So now I'm going to use two things. So first, y squared. Y is either plus 1 or minus 1. So what's y squared? Anyone want to guess? 1. Okay, good. So y squared is 1, so I can get rid of that. All right, and then we also have this quantity here, which is kind of annoying. We've got yi times xi times vk, right? So let's remember what this is. Xi times vk, that's the thing I used to make my prediction, okay? The one thing I know about this is when I made the mistake, right? So this is the time I made the kth mistake. So one thing I know is that prediction was wrong, okay? So in other words, I had the wrong sign. So either yi was positive and this was negative, or yi was negative and this was positive. In either case, when I multiply those together, I've got something negative. Then I multiply it by 2, and again, I have something negative. So I've got this, and this simplifies to something negative. So I can drop it, and again, make an inequality here. I know that this x squared here is no more than r squared, because that's another one of my rules, and I'm done. Okay, so this is basically proving that I'm not basically getting this improvement in my projection along u by just stretching this out further and further and further. All right, now can we use this to actually complete the proof? It turns out we can. We basically have these two things. I'm saying the inner product with u grows slowly, and the inner product with the hypothesis with itself grows, the inner product with u grows quickly, at least k gamma, and the inner product with itself grows by at most kr. That should be kr squared here. All right. Do we have that fixed here? Yeah, okay, kr squared. So let's just kind of put these things together, okay? So let's just take this guy and flip it around and square it. All right, so I've got this quantity, and then we'll just kind of simplify that. And I know that the norm of u is 1, so this kind of goes to that, right? And then I've got this other quantity here, v squared is kr. Okay, so I'm using that. Now I basically take this quantity here and plug it over here, and from lemma 2, I know that's no more than kr squared. All right, so we get rid of that, and now we've got this quantity. All right, so it's quadratic in k on one side and linear on the other. Okay, so if I divide through by k, I get this quantity here, and eventually I get to k is no more than r squared times gamma squared. Okay, so this gives an upper bound on k. K is the number of mistakes. Okay? And that bound depends on just two things. It depends on how big the examples are, because that controls how far out from space, from the separation plane. All right, and it depends on gamma. So the smaller gamma is, so the vaguer the examples are, the less well separated the data is, the larger k will be. Okay. So another way of writing this would be r over gamma squared. Okay. So this is a really interesting result. So it doesn't have anything to do with the dimension of the problem. Okay. So I didn't tell you. I never used what the actual dimension of x was. Right. X could have 10 components, right? Or it could be a vector with 16 trillion components, like in the experiments I saw before. That doesn't matter. All that really matters is r, okay? And if you kind of think about it, r is very closely related, or you can bound r by the maximum value of a feature and the number of non-zero features. So if you have all binary features and everything has like, at most 100 features, then, the maximum size of r squared is 10. So that's in it's some interesting way kind of related to sparsity, but not to the actual dimension of the problem. Okay. The other thing that's interesting is it depends on how, in some sense, how easy the data is, how big the margin is between the positive and negative examples, and that's all you need to get convergence. Okay. And I guess the other thing is it clearly makes sense for both of those things to be involved, because what matters here in some sense is, what this is basically telling us is that what matters is the amount of this circle that is, the ratio of the size of this circle and the size of this yellow stripe. Okay, so if the circle is really big and the yellow stripe is small, right, then it's a hard problem. Okay, things are kind of separable. Things are hard to separate. If the yellow stripe is big and the circle is small, it's an easy problem. Things are very well separated. All right. And if I change one of those without changing the other, right? It's sort of, if I change both of those things at the same time, if I took this picture and instead of projecting it up on the board, so it's like 3 feet high, I just looked at my laptop where it's only an inch high, or you looked at your phone where it's only like 1/4 of an inch high, right? Just scaling things up and down like that shouldn't change the complexity of the learning problem. And that's why it's kind of nice that it's basically the ratio of those things that affects the complexity. Okay. So questions? Here are online notes that kind of go through this. So this is a really nice proof, okay? So it basically shows that if there is something which classifies the data well, okay, then the perceptron algorithm a finite space, okay? It doesn't depend on the classifier. Okay? We can still hide. Don't worry about VC dimension. That's not important. So this doesn't prove that the algorithm is optimal. It shows that it converges, right? But we might be able to converge faster. And in fact, there are lots of algorithms that that vary this and have tighter theoretical bounds. One thing that's kind of practically important is we don't know what happens if the adversary isn't quite as nice. So in my rules, the adversary has to give you a label relative to you for every single example. So there's no choice, right? The adversary is staying away from the margin, from certain examples, and as also he's never giving you an incorrect label. So one question happens if the adversary does give an incorrect label. Well, I mean, if everything they say is incorrect, then it's going to be hard to learn the correct hypothesis, right? So obviously there still have to be some rules here, okay, to make the game of application interesting. And it turns out there's an interesting which argues that it is possible to use exactly the same algorithm and it will be robust to a certain amount of noise, okay? So here's the trick, and I'm going to come back to this, well, what classifier to use after learning. So this is really changing the data and I'm changing the algorithm, but really I'm not just a mental exercise, all right? This is a thought experiment, all right? So it assumes I can separate the all right? So one way I could is to add like a feature that was unique. So example I for that one. All right. So if I have n examples, I'm going to add n new features, all right, onto the end, right? So this first feature will be present in the first example. The second feature will be present in the second example and not nowhere else, and so on and so forth. Okay? And the weight I'm going to give it is some number, which right now we're going to denote by this capital delta, this triangle. Okay, we'll figure out what that number should be later. Okay? But notice, if I wanted to separate the examples perfectly, I could basically just use this part of the feature space, right? So I could set all these other features to 0, right? And I could just put a positive weight on all the positive examples, a negative weight on all the negative examples, okay? And how big does that weight have to be to get the margin? Well, it depends on what gamma is, right? If gamma is small, I need a big weight. If gamma is small weight. But by doing this, I make the data separable, okay? If that value delta is big enough. So let's kind of walk through the analysis, all right? So my old example X gets replaced with this new example that's got basically, n new features, but only one of them is non-zero. So basically there's one new non-zero feature. Okay, so in matrix formulation, if my old data matrix was X, now it's X, and I paste it on the identity matrix multiplied by delta, the scalar. Okay, so these examples are no longer guaranteed to be within a circle of radius r from the origin. Okay, but not too much further, right? I've just added one delta, so it's like r squared plus delta squared, not too bad. Okay. So let's look at this. Now let's figure out what I want to use for delta. Okay. So each of these examples needs to satisfy this margin requirement. Okay. So let this number di be the amount by which that example fails to satisfy the margin requirement. Okay. So if yi times xiu is negative, okay, then what I'm basically going to do, or it's smaller than gamma, right? Then I'm basically going to say, well, let's let di be big enough that it's going to be at least gamma. So that's what di should be for each example, all right? And now let's imagine what my hypothesis should look like, okay? So the hypothesis, I said we could just use the delta features, all right? So let's refine that a little bit. Let's just use the delta features just enough to get to a separation of gamma, okay? So to do that, I'm going to put a weight of d1 over gamma, y1 times d1 over gamma for the first example, right? y2 times d2 over, not gamma, delta over for the next example, and so on, okay? So the claim is if I do this, separated the, my claim is that this new data set here is now separable, okay, with margin gamma, all right? So I can put just enough weight so that I can get a margin of gamma on each of these things. So I've very carefully defined my secret hypothesis so it does separate things with margin gamma, all right? So this now gives me a new set of examples. The adversary can label them any way they want because I'm going to sort of compensate with these DIs. And these new set of examples are separable by this new thing of size u. All right, we have a mistake bound which we can work out. So there's a little bit of math that we have to do here because I've increased the size of u a little bit, so I've got to scale things down. But we can basically make delta be this quantity right here, and then we get a relatively nice formulation here. So if d is basically the norm of all this little, all these little values that I had to add to each example to make them separable, then I can separate, and the mistake bound will look like this. Okay, so this is an analysis, and it's based on this sort of hypothetical situation, right? I've gone through, I've labeled all I've extended all the examples with an ID feature, and then I've shown you the mistake bound that we can get here, all right, if I gave you these modified examples, okay? You could actually use this as a new learning algorithm, right? So I could basically, every time I get a new example, I can sort of extend the feature set, add a few more things, right? I could set it up this way, but it turns out I don't even have to, right? So if we look what happens with the actual perceptron algorithm, what is it going to do differently if these features were present? Okay. Well, one thing we know it would do differently is that it would have this mistake bound. Okay, so we can say something about how well it would do if I extended the example this way, right? If I gave it these new features, it would have this mistake bound because there is this unknown hypothesis u which satisfies this margin requirement, right? And everything is within this r plus d radius. Okay, so the hypothesis would definitely satisfy that mistake bound. Okay, but what would it do differently predictively? Okay, so remember at each stage, the hypothesis that we're using so far, okay, is going to be the sum of the examples that we've made mistakes on, you know, or with a factor of 1 or 0, depending on what kind of mistake we made, right? So the hypothesis is going to be a sum of the examples we've seen so far. So when I get to the mth example, example m, the weight for this ID feature, the m ID feature, is going to be exactly 0. Okay, I've never seen that feature before. Okay, so I've never added any weight to that component of the answer vector. Okay, so it's always going to be ignoring these ID features. It's not going to do anything different. Okay, so perceptron on this feature space will make exactly the same predictions as the perceptron on the original feature space. So this says, without changing anything, without adding all this nonsense, right, is still going to have this mistake bound. Because if we did add these features, it would have that. And if we did add those features, it also would not behave any differently. Okay. So that's the second observation. So this is actually a little bit more robust even than we think. All right, it's also robust to noise. So the conclusion we can get here, noise is okay. And the kind of noise that's allowed is really very much like the kind of the slack variables in SVMs, if you guys know about that. All right. So questions? All right. I'm going to lay one more bit of So far what it's kind of a funny thing. I haven't talked, usually we talk about learning, then we have a fixed classifier, you know, we distribute it to the servers that do spam filtering or something like that, and you know, it performs out in the real world. Okay, so here all I've talked about is this online learning process. It's updated whenever there's an example. I don't really know what after I've done this, it's not obvious what classifier to use for new prediction. Okay, so there's a trick called the average perceptron, which answers that question in a really nice way. So just to motivate this, supposing I have a sequence of behaviors. So I make a guess using my first hypothesis, which is all zeros. I get it wrong. So I make a mistake, right? Then maybe I get the next couple things right, and I make another mistake. So I update my classifier. Now I've got V2. All right. Then I make a few more things right, and I make a mistake. Now I've got V3. Okay. Then V3 is right once, and then I get a new update, and that's wrong. So now I have V4. Okay, so that's my training sequence. Now, what do I want to use? One possibility is just use the last thing that the learner had. So that's V4. Okay, but V4 is kind of weird. It's never really been tested on any examples. It's like sort of a brand new hypothesis. And of course, since we're adding the whole example to the weight vector at each point, these weight vectors kind of jump around a lot. All right, so V4 might actually be not a very good hypothesis. All right, so another possibility was I could look at things. Well, let's pick the that basically to do best on training data. All right, so there are five hypotheses I've used: V0, V1, V2, and V3. So V2 was right 3 times out of 4 that I used it. V1 was right 2 times out of 3. V3 was right, 50% of the time. So the one that looks best is really V2. Okay, so I could say I'll pick V2. All right. So there's another strategy, okay, which is to do a weight prediction. Okay. So I'm going to look at all these. Okay. I want it random according to how much of the data they were used for. So basically, that's how many examples they were sort of active for, right? All right, so V2 would be used, 40% of the time, and V1 would be used 30% of the time, and so on. Okay, and then after I make a randomized choice, then I make my prediction using that example. Right? For things that persist a long time, and there's a really nice analysis. So if I look at the error rate of that predictor on this data set, so the probability of making an error, okay, would be the probability that there's an error. Well, it's sum over, we marginalize that over k. So the probability of picking out, the probability, we pick k, right? Which is basically mk over m, where mk is the number of examples that vk was used for. All right. Then the probability that we make an error given that is 1 over mk, because we always make a mistake the last time, right? So we can simplify this, and we can see the probability of an error is k over m. So k is the number of mistakes. All right. So this randomized algorithm seems to work pretty well as a strategy. At least it sort of seems to have a low error rate on the training data. There's actually a deterministic approximation of this, which is even nicer. It's very convenient to do. Basically, what we'll just do is instead of choosing a weight vector non-deterministically with probability m is I'll add up all the weight vectors with weight mk over m. So I take a weighted average of them and then I predict with that. So I'll just predict using this v star, which is a weighted average of all these. So there's no theory for why that works as far as I know, okay? But it actually works. So this is, these are some experiments using these perceptron algorithms. So this is using the last one. So you see it's doing better, but it bounces all over the place, all right? This is using the voted perceptron, and this is using the average perceptron. Which line is which? I can't really tell me apart. They're very, very, very close. And this is very common. Okay. I want to jump ahead, even though we're like, I know, getting close to time. I want to talk about, well, let me actually stop here. So there's one example on the quiz which talks about this next section. I think I'll just take it out and use that for next week. Okay. So I don't want to like give you guys too much math in one go. All right. So this is sort of like the key kind of formal results, and then we'll get back to like efficient implementation and parallelization next week. Okay. So I'll see you guys on Tuesday.